In this video, we are going to talk about CANOpenNode and specifically about CANOpenNode implementation on STM32. Um, in this video, we are going to discuss some basics of CAN, and then we briefly go over CANOpen concept and CANOpen architecture, and then we start porting the CANOpenNode for STM32 microcontrollers. Also, we cover EDS Editor, and we also prepare a sample project with a couple of CANOpen nodes in a network, and we'll demonstrate that as well. Just to note that this video is not going to discuss very deeply and very detailed about CAN. It's just a very simple overview, but I'll include some links in the description so you can follow those links to learn more about CAN and CANOpen concept. So this video is just an overview on very simple stuff. Okay, so when we are talking about communication between two devices or a network of devices, so what we are talking about is just transmitting some information from one node to another node. So in that case, which is the first case here, we can use UART, we can use I2C or I2C, we can use SPI, we can use CAN, USB, Ethernet. All of these will probably work for this case. But the issue is that as we would have more devices in the network, let's say like here, then, for example, UART is not working because, a simple UART is not working because it's not created for network topology. So basically, it just can do some P2P communications. But still, I2C, SPI, CAN, they all can handle this situation, and they usually need to be in a master-slave topology where one master will pull for other slaves situation like status and then ask them if they have some data to send. So that's that's how it works in these cases. But let's talk about situation where we don't want to have a clear master in the network. So in that case, let's say device A has some information, it can just transmit those information, and then immediately after that device C has some information and it can transmit those information as well, and it doesn't need to wait for the master to pull its status and then ask a permission, for example, to send some information. So that's where I2C and SPI and USB probably cannot work, because in those cases we need a host or we need a master, but here, for example, CAN and Ethernet are good candidates for this type of communication, where each device in the network can basically send some information over the line, and the physical layer will take care of the assigning the bus to a specific node at any point. But usually Ethernet in these cases is a, let's say, it's an expensive option. So just imagine in an embedded board, if you want to have like Ethernet on a board, you need a very huge circuit and expensive probably IC to handle those Ethernet packets. But CAN, on the other hand, is a simple network. It's very simple though, but it can handle those situations. For example, let's say you have a console, or let's say in a car example, you have many sensor nodes and you just basically want to collect some information from this sensor, and some let's say ECU or central units, they just need to get those information or transmit some information, or there are some sensor node, they just transmit some information. So you see in these cases it's a very simple communication. We don't need very complicated network scenarios. So in these cases, CAN probably would be a better choice compared to Ethernet. So in a general term, let's say a CAN device, a device that is using CAN can have these types of architecture. So let's say this is a PCB of a device A, and it's let's say has a MCU or microcontroller. For example, in many MCUs, we have the CAN controller inside the MCU itself. For example, in STM32 case, we have many STM32 family, basically microcontrollers, which they include the CAN controller on the chip itself. And then for these cases, you just need the CAN physical layer to be able to communicate over CAN bus. Okay. But there are some microcontrollers, even in the STM32 family again, that they don't have the CAN controller. So in those cases, you can just put a CAN controller on the PCB. So it's an IC, let's say, and then that CAN controller will communicate over CAN bus via a CAN physical layer. So that would be another case for CAN communication. And let's say, for example, for a Raspberry Pi or for a other embedded system which are running on Linux, they usually don't have the CAN controller on the chip itself, and then you need to put the CAN controller on the board, and then they communicate over CAN bus same way. So yeah, that's it. So there are, let's say, two types: CAN controller on the MCU and CAN controller outside of the MCU. Okay, so let's see what is CAN controller and what is CAN physical layer. So you see, as you can see here, a standard CAN frame basically consists of many parts. So like ID, control part, data, and CRC, ACK, and end of frame. Okay, so the CAN controller basically generate this, okay, and it can handle the reception of this as well. So basically it can generate this and transmit it over CAN bus, and then if it's received something like this, it just basically parse that CAN frame and then just tell us, okay, we have a new data with blah 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 ID or with some data on it, and this is the CRC for that. Okay, and usually, as far as I know, in most of the CAN controller, they check for the CRC themselves. Okay, so yeah, you can see the more detailed CAN frame here. And okay, so CAN controller basically generate this or receive this, and then it goes, if it's transmitting this, basically it goes through the CAN layer, CAN physical layer, which basically generates two lines, CAN H and CAN L, which is CAN high and CAN low. And basically that will generate a differential pair signal where we can basically take it wherever we want, and as it's differential, it's more immune to noise, and it can be a long, let's say, wire or something. So yeah, so that's the job of the CAN physical layer. And on the other hand, just let's talk about the reception mode as well. So if we have a CAN physical layer, if it receives a CAN H and CAN L signal, it will basically translate those to a CAN RX signal, which, if you want to just imagine it, it can be a simple UART reception, let's say like this. So yeah, so the physical layer can transmit information and can receive information for the CAN controller. All right, so let's go to the next slide. So here we have the CAN network that we were talking about. So we have three devices that they want to communicate with each other, but there are some challenges here. Let's say, okay, so first let's discuss the basic communication. So let's say device A wants to transmit a CAN packet. It basically generates that CAN packet using the ID that we provided, and then it just transmit that CAN packet with the certain ID and certain data onto the line. Okay, and then others like device B and device C will receive those information, and it basically tells the MCU, okay, I received a packet with this ID and with this data in it, and it was, the CRC was okay, so you can use that information. Okay, so it's the very basic example, and basically at any point any of these devices can basically generate a CAN packet. Okay, and the CAN physical layer will take care of the collision. So basically using a method called arbitration, it decides which packet should transmit first, and then immediately after that the next packet can also be transmitted. Okay, so this is perfect for us up to this stage, but let's talk about a bit more complicated scenario. Let's say device A is on the line and is communicating with device B, and then device C will be added to the line later on. Okay, in that case, how are we gonna know that the device C is on the line? Okay, so let's say device C will transmit a startup packet at the beginning when it turn on or when it connect to a CAN bus, and then others will know about that. Okay, so okay, that's a perfect example. But what if we just disconnect the embedded device C? Then how the others know about it? So okay, we say, okay, we change the scenario, not on the startup, but every 100 milliseconds, let's say, we transmit a packet, let's call it heartbeat, and then others will know about it, and when they don't receive that heartbeat for a while, they know that device C is not on the line. Okay, so that works as well. Okay, but then we should write all this code for the for each of these devices, right? So you see the point. So it's getting a bit complicated. Let's talk about another scenario. Let's say device A is working at 125 kilobit per second. Okay, so and device B is also working at 125 kilobit per second, but device C doesn't know that, so it just comes to the network, like probably plugged into the network, and then how does it know like what is the baud rate? How does it know which ID it should use? So you see that the situation is getting a bit more tricky. So it needs some control mechanism that basically tells it to run at what frequency. So it's getting more complicated here. Let's say embedded device B has some variables, okay? And device C wants to read those variables or write those variables. So okay, we generate a packet with a certain ID, and then device B take that package and knows that, okay, if there would be an object, if there would be a CAN packet with certain ID, it means that they want to write some information in the variables that I have. So it basically do that. But as we go forward, you see the complexity is increasing. So that's where CANOpen comes in. So CANOpen is a standard that basically created many years ago, and this CANOpen standard basically take care of this. So it take care of heartbeat, it take care of configuration change, it take care of variable access, and basically it provides us the read and write to variables. So in simple terms, CANOpen is not like a magic here, it's just a set of rules and a source code and probably some stacks that basically handle this situation, and they provide us many more features. As we go forward, you will understand those as well. So yeah, this is the idea of CANOpen. So that's why we want to have CANOpen. So CANOpen, basically, if you imagine a device here, we have our application code running on the MCU, and then we have a CANOpen stack. Okay, so CANOpen stack consists of two main parts, let's say the object dictionary and the code and the logic basically in that. So there are many things here that we can discuss, but I don't want to get into details here. So we have a state machine, will take care of the state of the device. So when, for example, a device turn on, it goes to the boot up mode, and then startup, and then initialization mode, and then pre-operational, and then operational, and then it can basically stop as well. So that take care of that. CANOpen stack will take care of those commands and basically tells the application layer that we are in which state. Okay, we also have the two, let's say, important one is SDO and PDO. So we'll discuss this as we go forward. So basically using STO and PDO, you can any basically device on the CANOpen network can access some variables in the object dictionary, and they can update those variables. And then, for example, let's say device B can access variable 1 here and can change that, and then application that is running on device A can let's say, somehow informed of that and then can read the data from variable 1. Or let's give a practical example. Let's say we have this device A, which is a, let's say, central unit, okay, and it wants some sensor information from device B and device C. So device B and device C here will constantly update the variable 1 and variable 2, okay, and then application on the central unit just read those values. It doesn't care where those values are coming from. It just read those values and knows that those values are basically the last sensor value that that the other device B and device C transmitted. Okay, so this is the basic idea of the CANOpen stack. But as I said, CANOpen has many more features. For example, the sync feature, which basically it will synchronize all the devices in the network. Again, let's go back to the example that I provided previously. So let's say the central unit, which is application here, waiting for some variables from device B and device C, but it's very important for the application, central application, to get those information at a certain time and at a certain point in time, let's say. So it basically, device B and device C will be configured in a way that they will transmit those information right after they received a sync package. So they receive a sync package, they transmit the last sensor information, and basically the central unit will use those information and process based on those. Okay, so that's another basically idea of CANOpen stack, another, let's say, feature. Or let's say we want to have many devices on the network, so CANOpen stack will take care of device IDs. Okay, so let's say in a standard CAN without CANOpen stack, we don't have device IDs. We have a CAN ID, but that CAN ID doesn't mean that it's a device ID, you know, so it can be anything. But in this CANOpen stack, we have device ID or node ID, let's say, that basically you can put some filters, and then your device doesn't need to answer or receive, let's say, all the packets that are in the network. Also, device ID provides us this opportunity to have P2P communication. So let's say a central application wants to update a variable on device C. So basically it knows the node ID of device C, which is, let's say, C. So it just initiate an SDO communication, and it directly talks with the device C and basically get acknowledged from device C. So for example, it tells the device C to write variable, let's say 3 in your configuration, and then device C writes that value, and it basically confirms that it did write the value, and central unit knows that, okay, this task was done. So this is very, like, as I said, this is very simple introduction to CANOpen stack, and you can kind of understand now how the CANOpen stack works for you. Okay, so just another example. So as we go forward, I'll keep more example, but yeah. So in CANOpen OSI model, we have this data link and physical layer, which are not part of CANOpen. And then we have network layer, transport layer, session layer, presentation, and application layer. So for these two parts, we have the standard. So you can just check CIA 303, if I'm not wrong, or 302. And then basically that provides the information that regarding these two layers. Okay, and then we have presentation layer, which talk about the managers in a network, because we can have managers. It's a bit different from master slave mode. It's basically more like manager of the bus and the network. It's a bit different. And then we have these CIA 401 and 402. Basically, they are talking more specifically about the device itself. For example, 401 talks about the I/O modules, devices that they have input and outputs, and basically you can control those. Or another one is talking about motor drivers. So if you are making a motor driver, you should, and you want to have CANOpen, let's say, let's say logo on it or certification on it, you should follow those instructions that they are saying for motor drivers. Okay, so in the application layer, they're specifically talking about application. So you can check all those information. They're freely available on internet. Okay, so now let's talk about the object dictionary. So as we discussed, object dictionary is basically a group of, let's say, variables in simple terms that you can basically access from the network, but you define those let's say, accessibility. So for example, you can give access to any nodes in the network to read something or to write something or do both. So it's in an order predefined fashion. Okay, so basically you can just define everything, and then those objects basically includes data that basically have direct impact on the application or communication. So object dictionary also includes variables. So of course, variables we talked about, mappings, and configuration of the device. So basically you can configure node ID, the baud rate, and all this stuff in the configuration. Okay. Yeah, usually we generate the object dictionary automatically by a GUI, which we'll talk later. It's called EDS Editor in the CANOpenNode stack. We'll talk about this more as we go forward. But just for now, know that there is an object dictionary. It basically holds the variables and configuration for the device, and we generate these object dictionary using a GUI, and then CANOpen stack basically use that for configuring the CANOpen stack. Okay, so let's go to the next slide. So we have a couple of concepts that I would like to discuss before going to the practical part. Okay, so in CANOpen we have the emergency package or the emergency object, which are basically triggered by CANOpen device internal error. So basically, if something goes wrong in the CANOpen stack and also application, we can basically generate emergencies, and it immediately will be transmitted over CAN bus. And emergency packages are usually having the highest priority, so they will basically immediately will transmit over bus, and they are transmitted once for each error. And yeah, that's it. So we have the heartbeat. So heartbeat basically, as we talked a bit before, so basically they're periodic packets that are transmitted in the network, and basically their main use case is to basically inform others about their situation, and then we can do very cool things with them. So basically we can tell other nodes in the network to listen for the heartbeat from a certain node, and if they didn't receive that heartbeat from a certain node, sorry, they just change their state to, let's say, pre-operational. So that's called basically node guarding, which you might do in the tutorial. We have the boot up. So the boot up message is basically the first message that CANOpen stack generates to inform others about its existence in the network. Okay, and it will be transmitted just once on the device initialization. We have, okay, so now this PDO is, I think, one of the most important things in the CANOpen. So PDO are basically some packets that we transmit in the CAN bus, and they can be transmitted by any node, which basically kind of act as a broadcasting an information. Okay, so let's say, let's give a practical example, because usually I prefer to give and to also receive practical example. Let's say you have a node, it basically measures the temperature, and it wants to transmit it. Okay, so we can just make a PDO in the CANOpen stack, and basically we just tell the CANOpen stack to transmit this temperature over the CAN bus every 100 milliseconds. So every 100 milliseconds we'll update the temperature, and we'll transmit it to the CANOpen stack. So here, any node that needs this temperature information basically takes that information and save it into the their object dictionary, and then their application might use that. Okay, so just simple terms, one node generate PDO, and it will transfer it to the CAN bus, and any nodes in the CAN bus can subscribe, let's say in simple terms, subscribe to that PDO, and they can receive it and map it to the one of their variables in the object dictionary. So that's the idea of PDO. So PDOs are usually, let's say, real-time data transfers compared to SDOs. They usually don't have protocol overhead, so they're just a simple packet consisting of 4 bytes, and they will just transmit in one go, and that's it. Yeah, as I said, usually the use cases are transmitting real-time values from a node to other nodes, or receiving real-time values from other nodes. Okay, so it depends. If it's TPDO, it's a transmit PDO, and we usually transmit these from a node, and other nodes will receive that, and in those other nodes will define a RPDO, and that RPDO basically get that TPDO and writes it to the object dictionary. Okay. Yeah, it can basically map to specific variables for automatic transmission or reception by stack. So basically you can make a variable, and you will see this as we go forward. In the EDS editor, we make a variable, and then we map it to a PDO, and we'll tell the PDO, we'll tell the stack to transmit that PDO every 100 milliseconds. Okay, so and that basically will be transmitted in every 100 milliseconds. On the other hand, on the receiving nodes, we'll make a RPDO. We'll make a variable first, let's say, and then we'll make a RPDO, and we'll tell this CANOpen stack to, if you got this PDO, just copy that value and put it in these variables. Okay, and it will automatically do that for you. So PDOs can be triggered by events, so you can write the code in, you can trigger them by the code, or they can be transmitted by timer. So you can tell the CANOpen stack to transmit them every 100 milliseconds, or they can be asked remotely, which I should note that in CANOpenNode stack we didn't implement that, so we don't have remote node PDO triggering. Okay, or PDO can be transmitted by sync object. So basically, whenever a node receives sync object, sync packet in the network, it immediately generates the PDO after that. So that's it. Let's go to the next slide. So SDOs. SDO, let's say if I want to compare, let's just very bad example, but I think it's help you to understand. So if you want to compare it to the networking, PDOs, sorry, PDOs are like UDP packets. Okay, so you just transfer them. Also, although in UDP packets you may specify the destination address, but in PDO we usually don't do that, so we just broadcast. Okay, so we broadcast a UDP packet, and whoever interested in that packet will basically copy those information. Okay, but in SDO we have a similar concept to TCP. So basically the destination is predefined in the message itself. So let's say it's a more like client and server. Okay, so in this case, though, we have a bit more different idea. Okay, so the client knows the address of the server. So the client initiate a packet, let's say ask the server to give a certain information to the client. Okay, so in this SDO we have this client and server. Client is usually the one who initiate the protocol, and server who is basically serving and responding. Depending on the scenario, it can respond, it can react based on that. So let's say we have a new node in the network, and it's not configured yet, and let's say for the unconfigured node we have the node ID of 1, and then whoever is with the ID of 1, we want to update its node ID to, let's say, 3 or 4. Okay, so basically we want to update a variable in a node, let's say here node ID 1. Okay, so basically a master or a manager in the network will basically initiate an SDO communication and ask the node 1, which here is the server, and ask it to update its node ID to, let's say, 3 or 4. Okay, so here we have this SDO, and we talk directly P2P to the node that we want to update its ID. Okay. All right. So yeah. So with SDO we can target a certain node specifically. It's not like PDO, we generate a packet and everybody listen to it. Actually, everybody can listen to it, but in SDO we have this ID and we specify the ID. So a certain node will just take that value and respond to it. Although I'm saying as it's transmitted over CAN bus, everyone can receive it. But in CANOpen stack, that certain node with a certain value will respond. Okay. Yeah, it's usually used for transferring large block of data. So it's very good for transferring large block of data. Why? Because we have this acknowledgement. So basically, when you're talking to a node, they acknowledge and confirm the reception of data. So that's good because, for example, let's say we want to transmit a very important information and we don't want to lose anything in here. So we just basically use SDO to write that large amount of data to a node. Okay, so that's the use case. But usually it has a very like I wouldn't say very big overhead, but it has overhead. Okay, because like we depending on the situation, we might ask the client to prepare itself, and then we send the information, and then we ask it acknowledgement. So you see the many packets are passing through here. So that's the overhead. Okay. So use cases, as I said, you can use it for configuring a node parameter on a startup. Let's say you want to configure a motor driver. You want to set the voltage, you want to set the current. So that's where you use STOs. Okay. For transferring large data blocks like framewares, you can use the STOs. For peer-to-peer or P2P, reliable communication, because as I said, we are confirming each packet, so it can be used for peer-to-peer reliable communication. Okay. And then we have the NMT. So NMT is a very general concept in CANOpen. It's basically a network management, not a network management, but basically a set of network management objects or packets that we are sending through CANOpen bus. And that NMTs, for example, can be, again, a practical example. Let's say we turn on a system, all the nodes go to the pre-operational mode because they're not configured yet, and we start to configure them one by one. Okay, and then when we finish configuration, we'll transmit the NMT packet and ask everyone to move to the operational state. Okay, so that's where we use NMT. It basically it has more features. I don't want to get into details, but yeah, that's the basic concept of NMT. So NMT is network management stuff that are going on. Okay. Okay, so now let's talk about CANOpenNode. So CANOpenNode is an implementation of CANOpen, and it's a software written in C, and it's available on Linux, PIC or PIC microcontrollers, and also STM32. So in STM32, we have this architecture. Basically, it's not just STM32, but basically in all of the ports that we have for CANOpen stack. But in STM32 specifically, we have this routine. Okay, so when the program starts, we have this CANOpen app init, which basically will initialize different parts of the stack, and then we have basically 3 routines and 3 functions that will be basically run kind of concurrently. Okay, so we have CANOpen process. It basically do the processing of time-consuming tasks. For example, if we have an SDO, if we have a change in network state, if we have updates to the LEDs, so it will take care of those and basically handles those situations. Then we have CANOpen app interrupt, which basically it's the interrupt made by a timer. So in the CANOpen node stack, we have a timer, or we have, let's say, a real-time thread that needs to be run every 1 millisecond. It's configurable. I'm just saying 1 millisecond just for an example, okay? So every, let's say, 1 millisecond, we have this interrupt called, and then it basically quickly check for PDOs. It checks for, let's say, PDOs who are waiting for transmission, okay, and then copies those like in received PDOs and process them and put them into the OD or object dictionary, and also it copy the PDOs that are ready to be sent to the CAN, and basically it also just generates the sync packets. Okay, so you see these tasks are kind of time critical, so we need to do them at a certain point. So that's why we have the interrupt here, and yeah, that's it. And we have also CAN interrupt. The CAN interrupt is very simple. It just respond to CAN receptions. So if we receive a packet, we need to take it out of the buffer as quick as possible. So we have this CAN interrupt here, which basically empty the CAN reception buffer. It partially processes the received packet, but just to know like what is this packet and if it's related to our node or not. And then yeah, that's it. Basically, it's just put it in a certain buffer for the CAN app process or CAN app interrupt. Okay, so CAN app process or CAN app interrupt basically take care of those reception, take care of the processing of those receptions, to be exact. Okay. Yeah, that's it. So yeah, if you have an RTOS, you can basically call this app init in your task init, and then you can call this app process in your OS task loop. Okay, so that's the idea. Okay, so about the CANOpenNode code structure, we have this CANOpenNode repository on GitHub, and it basically have a couple of folders: 301, 303, 304, and you can see the description for each layer here. And basically you usually don't need to touch it. You just clone it using git, and then that's it. So that's the base of the stack. Okay, and then for STM32 we have another folder, which is the porting of STM32, porting for STM32, sorry. And it basically have these files, let's say. So we have CANOpen or CO app STM32, which basically is the most abstracted layer, the highest level, where you have the initialization and that app process and timer interrupt there. And then we have the driver, which is basically the low-level implementation of the driver for STM32. And then we have the storage, which in our case we didn't implement it yet, but you can change that based on your usage. For example, let's say if you have a SD card or you have an external E2P ROM, then you can basically implement the code for those in a storage block and storage blank. Sorry. Then we have this EDS file and XPD file. Usually use the XPD file for EDS Editor, and then basically it's the definition of the OD of the object dictionary. Yeah, basically you use that, and then using that you can generate the od.c and od.h. Okay, so these are the object dictionary files. So that's about the STM32 CANOpenNode STM32 code structure.
All right, so let's start doing some practical examples. For this purpose, I have the STM32G0, and this is the evaluation board. And then I have a STM32F4 discovery board and STM32F0 Noclo. And just consider that F072 has CAN. Other F0, I think, as far as I know, they don't have CAN. I mean, just check it, but this one has CAN. Then for the purpose of this tutorial, I'm using PCAN USB analyzer. It basically shows us the CAN messages. Then I'm using CANOpen Magic software. Uh, that CANOpenMagic is a commercial product, and it basically shows us the packets that are going through, and it basically interpret them for us to just know what's going on there. Okay, so that's about the things that I'm using, and yeah, that's it. Let's start. Okay, so let's make a folder here. CANOpen tutorials, and let's open a console here. Blah blah blah. Okay, the console is here, and now we need to clone the repository. Okay, so the repository that we are going to use is this one. So this is the official one. I'm keeping it up. I'm keep I sorry. I will keep it updated, but this is not updated for this tutorial. So most probably when you're watching this video, you just need to clone this repository, okay? Because I'm gonna merge my code with this one soon. But for the purpose of this tutorial, I'm gonna use my own repository, a fork repository. So this is going to be used for today. So I'm just going to clone this one, okay? So uh, git clone this repo, and then we need to cd into the repository, or I say repo from now because it's a bit difficult for me to say it very quickly. So let's cd into our repo, and then let's run the git submodule update. Basically, uh, this command will pull the CANOpen node stack, the whole code, and then it also pulls some of the libraries that are needed for the legacy example. Okay, so the legacy example here is basically an older example that we had, and then I just merged them together and make it like a whole uh, like a source code for all the microcontrollers in STM32 families. So, but I didn't touch the legacy one. So basically, if you wanted to have a look at the legacy one, you can use that legacy folder, and that legacy one is basically based on these couple of uh, libraries which are written by Thailand. So I didn't touch that, so you can basically have a look at them. But the newer examples are in the example folder, and you can have a look at them as well. And we are going to work with the newer examples today. Okay. So now I merged, I updated the submodules, and let's go back to the folder that we made. All right, it's here, and let's open STM32 Cube IDE. So here it is. Let's go to the open project from file system, and here we go. So C can open STM32, and I'm just gonna open all of the examples. All right, perfect. So here we have them, and I have my boards connected. Okay, so first step is to basically build the project. Hopefully they will build. All right, so apparently there's no issue. Now let's program it on the board. So I have 3 boards connected, okay? So let's go to debug configuration and then double click here, and then it quickly detect the binary file. If you couldn't see anything here, you just need to build the project and then refresh the project so you can find the binary files, okay? And then here we need to specify the ST-Link serial number because we have 3 boards connected, and we need to tell the the debugger which board it needs to connect and program, okay? So in order to do that, I open a STM32 Cube programmer. Okay, so it opened another monitor. All right, so this is the Cube programmer, and very easily, basically, you can have a look here. So I'm gonna program F01, so it's ending with 11 as a serial number. So I press scan and then 11, and that's it. All right. Before programming the board, let's open CANOpenMagic Professional. And so this is the software that I'm using. It's commercial, unfortunately, but it's a very good software, honestly. So let's run the tracing. So it basically shows us all the messages. And as we go forward in this tutorial, we are going to use this software more often. Okay. So let's start the tracing. Okay, it's running, and let's program the first board. Okay, so just press the run button there, and let's wait for boot up command, boot up packet, sorry. Okay. Oh, sorry, I forgot to connect the network. Okay, so we'll go here, we'll choose big CANOpen, and here we go. We got a couple of warnings from Node 24. Okay, no worries, I don't know what's that, but yeah, we got the, so probably they're just left over from other tests that I was doing before this tutorial, but yeah, don't care about them. So basically, if I reset the board, you'll see boot up command. You get error frames because when your board is resetting, basically the pins can be floated, and that's why you get frame error, but that's fine, no worries. You got the boot up from Node 24, which basically you can do, just have a look at the code, and you'll see it there. Okay, 24. Yeah, perfect. Okay, so that was very quick start. Okay, so I just did it to show you uh, where you can find the boot up message. Okay, so now let's discuss a bit about the code. So our code, basically, we have this main.c, and there here we have the initialization part, and then in user code begin we make a new instance of CANOpen STM32 structure. And then here we just pass it a couple of things that it needs to know. So it needs to know which can handle use. So it can be can handle type def, or it can be fd can handle type def. But the library takes care of that. So here it knows that we're using the can, so it just shows the can one. But if it shows you the fd can, you need to pass in the fd can one. Okay. Then we need to tell it about the hardware init function. So this hardware init function is basically the function that STM32 Cube MX provided to you, okay? Because we need it later when we are resetting the communication protocol. It basically called this function again to just reset the communication protocol and put everything in the normal state. Here we need to pass in a timer handle. Basically, that timer fires up. I mean, the interrupt fires every 1 millisecond, or even you can configure it to do a smaller step for more accuracy and less jitter. So this is the timer that we configured. And just a quick note that we'll go through all these in details later on when we are writing the code for our own custom board, okay? But in this example, I just want to quickly run over the code and tell you what it does. So here we pass in the desired node ID. Just note that the desired node ID is not uh, like, it's not the node ID that we're gonna have. We might change that. I mean, the LSS or the NMT manager, any of those can change the node ID. Okay, so just consider that this is the node ID that we want, but then the library later on gives you the a node ID that we call it active node ID, which is the node ID assigned to the node. Okay, so this is just the desired node ID. And we have the baud rate, and this is not going to have effect if you change it. It doesn't affect the CANOpen, because we define the baud rate in the CANinit, and we basically did it in CubeMX GUI. So here we just tell the stack what we defined, okay, what we set. It doesn't affect the, if you put 250 here, stack still works, but it thinks that it's running at 250, although it's running at 125. Okay, so just be aware of that. And then we basically call this canap init, and then we pass this configuration to it, and that's it. It initializes the CANOpen, and here we just need to call this function like regularly. Okay, so this function basically take care of can process, and then it also gets the status, basically LEDs state, and then you in your code you can use that, and you'll see that when we are writing the code for STM32G01. Okay, all right, that's it for this part, and this node is running. Let's run the F4 one. Or we might write that later ourselves as well, just for the demonstration. But for now, just let's run it. Okay, it's building the project. Okay, debug configuration. We need to know about the, okay, so the serial number will end at 53. Let's scan 53. Perfect. Okay, and here we go. Okay, it downloaded and ready. Let's check the boot up. Yes, we have the boot up as well from this node. And what we can do here is we can just click on network management, network overview, and then here we can scan the network. So basically what it does is that it just sends a SDO command to all the nodes on all the 127 nodes, and then to see which one will answer to that SDO request. I think the SDO request will read the vendor ID, or maybe device type ID. So here you see we have node 1 and node 24, and NMT status for them is unknown because they are not transmitting any kind of heartbeats at the moment. Okay, but if I just press this set a heartbeat, let's say every 2 seconds, as soon as they send their heartbeat, we'll see that their NMT status is going to be changed to operational. All right. Okay, perfect. So they're working. Don't mind the error frames now, because after some time that we're gonna have more messages, they will disappear. Okay, let's put this on fix so we just see the the updated version. So you see almost every 2 seconds they are sending their heartbeat status to us. Okay, so this is the second node. Let's go to the third node. Let's open here and basically press this button. Let's find the serial number. It's 45 at the end. Just pausing some moments to just skip the building process, because that's just gonna take some time and it doesn't really matter. So all right, so now let's choose the which one was it? Sorry, 45. 45, apply, okay, and this is going to be programmed. So let's have a look here. We have an emergency error from node 1. Uh, I don't know, for some reason this node 1 on my network acting a bit weirdly recently, so don't mind if it shows any error. I think it has some problems with the clock, so I didn't investigate it much, but this is going to cause some errors in future, so don't mind those errors. Okay. um it's not related to CANOpenNode at all, because it's just the CAN transceiver showing some errors. Like sometimes it goes to passive mode. But yeah, all right. So we got the boot up from that, and let's scan the network again. Here you go. Last thing, boot up, and we just press this again, so it sends us heartbeats every 2 seconds. That's perfect. Okay. So what's the next step? So we can go to the next step, and we can basically make a change. So let's do this. So let's make a new project with STM32G0 board, and let's port this CANOpen node to STM32G0. Okay. The porting procedure is going to be exactly the same for STM32 F1, F0, 1, 2, 3, 4. So it doesn't matter. Just for this tutorial, I'm gonna use STM32G0, okay? But it's gonna be same for STM32 F4 or any kind of board that you're going to be used, okay? So in order to do that, I'll close this sample here just to not make any confusion, and I click OK. Then I'm gonna connect to that board and raise it. So we make sure that this board doesn't have any kind of a CANOpen node on it. And let's check that with the CANOpenMagic. Okay, we don't have it. Perfect. That's all we wanted. So let's go. Let's make a new folder. We call it custom board. And here I'm gonna make a new project. So go here, new project, STM32 project. So it's downloading some stuff. So I just pause the video again to save your time. All right, that's it. I think now it's gonna, yeah, target, loading the target selector. Okay, we have it here. So for the porting, we're going to use a board from STM32. So I'm gonna just go here. It doesn't matter if you're not using any kind of specific board, you just do the initialization for your board. Okay, so STM32G0, STM32G0, C1E. All right, that's it. We'll select that. It's this board again. So location. I would like it to be oh, sorry. It's gonna be here. STM32G0 CANOpen. Yeah, CANOpen. And select the folder. Oh, sorry, I just wanted this. So I go to the custom board and then select it, and then here we give it a name. So STM32G0 CANOpen. And here it would be the same. Here we use this one. Finish. Yes, I want to initialize all peripherals in their default mode. Okay. We'll wait a bit. I just paused the video again. Okay, I think it's going to be here very soon. Okay, here we go. We have it. So as you can see, in case you're using a custom board, it's gonna have everything here, as you can see. And if you're using a sorry, if you're using an official board from STM32, they'll give you all the configuration. Or if you're doing a custom board, then you need to do it yourself. Okay, so I'm using the official board, so I have everything prepared for me. Not fully prepared, but kinda just assigned all the pins and stuff. So next thing is to use the CAN. So okay, I'm gonna run this sample on CAN 1, and that is going to be, let me just check that, connector number 12 on the board. Okay, so FDCAN activated, so I'll press this activated, and then what I need in this step is a 125 kilobit per second configuration. Okay, so I activate the auto retransmit. So basically, if it couldn't transmit a packet, it tries again, and it might be able to, I mean, we give it the chance to pause the transmission if it wanted to. And here we just go to this this part. This is the interesting part for us. Okay, so let's just check everything else. Classic format, yeah, we want a classic mode. We don't want to have the FD mode. We want to have a normal mode. Yeah, and then sync jump, we don't change it, it's just one. Data prescaler, so it's honestly, I don't know what's the difference at this stage between the data prescaler and the nominal one, but I'm gonna give it the same value for both. So we'll start with these and then we'll copy the same information up there in data mode. Okay, all right, so let's see. So our CAN is running at 60 megahertz. Okay, and our core is running at 60 megahertz as well. But let's change that. Just one would like to change that. So let's put 64. Ah, it cannot find any solution. Um, let's use us because it's on HSI. So let's put it on this PLL. Yeah, there we go. We got it. So we have 64 megahertz on FDCAN. Okay, so let's go back and let's go here. So I'm using a cool tool online. If you search for STM32, STM32 CAN calculator, you're gonna see this bit timing .can wiki info. Blah, blah, blah. So this one is very cool. I just select ST here, just give it 64 megahertz that we were using for the clock for FDCAN, and we want the sampling point at 87.5, which is for CANOpen, and we want the sync jump of 1, but apparently this is need to be 1. Apparently that's not used in calculation, so you just put it 1. Okay, don't care about the rest, and we will put 125 here. Perfect. So we press the request table. Here we go. We have the bit rate 125. We have the prescaler, segmentation 1 and 2. All right, we go back to uh, our lovely STM32 cube ID, and we put here 32. It was right, yeah, 32, I think. Let's see it again because I forgot. Yeah, it's 32 and then 13 and 2. So nominal 1, 13 and 2. Here we go, we have 125. So we'll do the same for data as well. So 32, 30 and 2. All right. Oh, I need to go and read about this data and nominal one. I honestly I don't know much about it. So that's it at this point. Alright, so we are good from the configuration point of view. Let's activate the FDCAN interrupts because that's something we're gonna use. FDCAN IT1 and IT0 and IT1. It's kind of shared between timer 16 and timer 17. So just be aware of that. And let's go and configure the timer. Okay, for this purpose, I'm going to use timer 14, and we need to know that timer 14, which APV is using. So we have APV1 and APV2, or no, actually in STM32G0, apparently we have only 30. Sorry, we have only APV one APV. So we don't need to check that. In case you are using another microcontroller that they usually have APV1 and APV2, you can just basically go into in their datasheet and then just find that. Okay, that which timer is you are going to be used. And here we have just one. So I guess that's it. Just quickly checking the other parts. Yeah, that's it, I think. Yeah, so it's 64, okay? 64 megahertz. So a quick calculation here. 64 megahertz. We divide it by 64 again, and then we divide it by 1000. So we reached 1000 basically milliseconds, sorry, 1000 countings, which basically means every 1 millisecond. Okay, because we did with the megahertz, so we are dealing with the microsecond, and 1000 microsecond is basically 1 millisecond. So let's put here 63, and let's put here 1000. And yes, that's it, I would say. We just need to activate the interrupt here as well. Is that it? Just let me think a bit. So we have the pins ready, we have the CAN ready, we have the timer ready. Just let's go back here because I have steps here. So we have the CAN, we have the interrupts, and we have timer, and yeah, we are good to go. So I save this project, and as it is the first time, it's gonna generate the code for me. Okay, so press yes and press yes. Here we go, we have the project ready. I'll close everything. Okay, here we go. This is the project. All right, we have the project ready, and now let's add the CANOpen stack. Okay, so in order to do that, I'm gonna take a bit weird route. So I'm gonna make a new folder here. I'll call it CANOpen stack, and I'm gonna clone CANOpen STM32 stack here. Oh, sorry. Git clone this one, and then I also need the CANOpen node itself. So again, CANOpen STM32 is based on CANOpen node, so I need that as well. So I do git clone CANOpen node. Perfect, we have both now. We just go into the folders, just take all the codes here except for examples, and or actually we can copy whole folder to our custom board, and then just remove the example for your own ease, okay? Because we don't need that. I also go to CANOpen stack folder, which we cloned, and I just copy the STM32 one because we don't need the examples and legacy, okay? So I just do that. Sorry. Ah, got lost in the folders. Okay, custom board, and copy and paste it here. So, okay, we're gonna have CANOpen Node and CANOpen Node example. Sorry, CANOpen Node STM32. Okay, so now let's add them to the project. Basically, since we made them in the project, they are just right into the project, okay? So let's refresh it. Yeah, here they are. And let's add them as a source code. Perfect. Oh, yeah, they're here. And let's add them to the includes as well, because they are including some header files that we need. So CANOpen Node and CANOpen Node underline STM32. So those are the folders that we need. Okay, apply. And here we go. We have them as a source for our project. Next step is to include, sorry, not here, maybe, include CANOpen app STM32 .h. And the next step is to initialize CANOpen node, initiate a CANOpen structure. CANOpen STM32, but just with the lowercase, okay? And then CANOpen STM32 instance has can handle, and we'll give it to so I think it's HFD can1, and then CANOpen has also hardware function, hardware init function, and assign it to, what is it, mxfd can, okay, can1 init. And then we also need to give it a timer handle, and edge time 14 will be that. And CANOpen again, desired node ID we want, let's say 32. CANOpen baud rate will be 125. Let's see what else we have. I'm gonna say that was it. So let's initialize that. Initialize CANOpen stack. Yeah, here we go. So I think we are good, and the only thing we need to do now is just write CANOpen process. That's it. You think that works? I don't know. Let's try it. So I build a project. We might have some issues because I'm just doing it right now. I didn't get prepared for doing this. So just imagine that it might have some issues. Okay, and I think the serial number was 45, if I'm not wrong. Let's just check that. 45, yeah. So, okay, just make it and then run it on the board, and let's hope that we're gonna see a boot up message here from node 32. Here we go. We have node 32 sending a boot up message. So basically we ported our CANOpen STM32 to this STM32G0. So I hope that would be easy for you to do as well, and hopefully we'll get that very quickly. So next thing I would like at this stage is to assign the LEDs on the board to LEDs from the CANOpen. So I have LED1, which is the green LED on the board, LED1 pin, and then we're gonna have CANOpen dot status screen. So status screen will be here, but as this LED1 is connected, like the common side is connected to VCC, when we want to turn it on, we should give it 0. Okay, so it's exactly opposite to what CANOpen stack provides us. So let's put the knot here. I'll copy the same and I'll put it here again, but this time with LED red and LED2. But I think LED2 is orange, but for our use case it's okay. So let's run it again. Perfect. I have the LEDs working as well. And in my case, the red LED turns off and the green LED will basically stay on. Okay. Uh, all right. So we did the first part. Now let's just scan the network again. All right, we have it in the boot up, but that's just consider that was the last thing we heard from Node 32. So if we want the current state, we should just ask it to send heartbeat. Okay. All right. So it's coming in. Let's clean here. Yeah, we have three nodes. Sorry, node 32, 24, and 1. They're just sending heartbeats and their status. Okay, so now let's read the device type. So we go to I just forgot. Yeah, read from node. Okay, and we're gonna read it from node 32. 32 here, and we're gonna ask it to send us the device type. Perfect. Let's do a read. All right, it's sending us 0 because we didn't assign it. So again, let's now read some other nodes. Okay, let's read node 33. Here we go. We get client aborted because we don't have node 32 on the line. So let's put it back to 30. Sorry, we don't have 33 on the line. We have 32 on the line. So read. Yeah, we got it. Okay, perfect. So that was the porting part. Now let's start with the OD uh, editor or EDS editor. So what I'm gonna do again, just come back here and let's go and find that OD editor. So again, I have a fork version of OD editor, okay, or EDS editor, and I'm gonna use that one. CANOpen editor, because this one specifically, the repo doesn't accept merging. I don't know, for some reason. So, or pull request. So I have the updated version, which I solved a lot of issues in my repo. Okay, so let's open a terminal. Oh, I just noticed that the terminal was open on another window, and I was probably cloning the things on another window and couldn't see it, but it's okay. So git clone EDS editor. So for opening this EDS editor, you must have the Visual Studio. If you don't have it, I always release the last version here, CANOpen Editor, and you can download that one. Okay. So, but just cloned it here. So let's open CANOpen Editor. As I said, you can use your use the compiled version and binary files, but I'm gonna use the source file. It's just loading up on my other monitor, but I'm gonna bring it here. Okay, excellent. Let's start it. Here we go. We have the EDS Editor. So it seems very simple, but it works good. So now open and let's go to CANOpen tutorial. We were working on the custom board, so we'll go there and CANOpen Node STM32 and open the XPD files. That's very important. Open the XPD file and here we're gonna give it a name, custom board tutorial, and we need to, yeah, that's it. We don't need to do much here, so we just save the project. We click on update and then we save the project. And then let's go to the object dictionary. So first thing, let's update the device type. We want to give it name. So sorry, device type. So we give it 30. Or no, let's do it like this. 1, 2, 3, 4. And this would be an empty, and it's gonna be in storage group of persist communication. So we'll talk about that later on, hopefully. So you can save some stuff in RAM or some stuff in persist basically storage, or you can even add more. Sometimes you want to store some configuration on a SD card, let's say. So you can just add that and then use that. But I don't want to make this tutorial very complicated, so I just stick to what we have now. So I'll just update that and let's save the changes, and then here we go. We go for generation for number 1. So custom board, then CANOpen STM32 od.h save. That's it. Let's go back to program, run it. Let's wait for the boot up message. All right, we received it. Now let's read the device type. Here we go. 1, 2, 3, 4. So just notice that we didn't change anything. Like we didn't change the source code. Basically, we just generated the object dictionary and basically we programmed the board using that. So object dictionary. So this object dictionary editor basically create the od.h and od.c file, and then we programmed that on the board and we were fine. So that was the first thing. So that was about the object dictionary. So basically you can change everything else. So let's do one more thing. So let's change heartbeat. So dun, 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 where we have the heartbeat. Yeah, producer heartbeat. Okay. So let's give it 1000. So every 1 second it should produce heartbeat. So just imagine now. Usually when a node boot resets, so if we reset all the nodes from here, so they all go into the, sorry, reset, not com reset. So if we reset all the boards, they'll all boot up, but they don't send a heartbeat message initially because they were not supposed to do that. and as you reset the board, you basically reset the flash, and basically in the configuration that they have for at the beginning, they don't have the heartbeat. So now what we want to do is that we want to add the heartbeat. Okay, so producer heartbeat, we gave it 1000. So just consider that that's in milliseconds, and 1000 millisecond means 1 second. So every second we're gonna have heartbeat from that node. Okay, the node custom board. So let's generate the od.h and od.c, and let's program the board again. Let's wait for the boot up message, and then hopefully node 32 should start transmitting heartbeats every second. So boot up, yeah, every second we have the boot up message coming, and it shows operational. Okay, excellent. That's what we needed. So let's go to the next thing. So let's add a, a TPDO. Okay, so transmit PDO, we talked about it. So these are usually the things that we transmit every like every now and then, like basically on based on what we want. So in this method we want to do the event model, which basically means that we're going to transmit a value or a counter like periodically uh, every, let's say, 2 seconds. Okay, so in order to do that, first thing we need to do is that our device gonna have a counter. Okay, because we're gonna send that counter value. So let's make a new value. So in order to do that, you just click here, left click, and then you click add. Okay, so it opened this window. So we need to give it a index. So I usually use 6000, and we give it a name, counter, create. So it basically generated a counter for us. And as we want to transmit this, we need to give it access to PDOs. Okay, so I give transmit access to PDOs. Save and Control S here again. So this procedure should be always the same. Save changes first and then Control S to save it. Okay, if you do it the other way, it just doesn't work. So let's go to the TXPDO mapping, because we need to map that value counter, right? So we come here, we should click on this one. So let's just check yeah, it's unsigned 32. So click here, first PDO, or you can make more PDOs, and we will do that later. So let's click here and choose counter. That's it. You see, it just used 4 bytes as it is 32 bit variable. And okay, so we wanted to transmit every 1500 milliseconds. So let's just do the calculation for that. So let's go to the programmer mode. 1500, it's gonna be 5 DC. So here we enter 5 DC, save, and Control S, and then let's export the od.c and od.h. Okay, I think something was wrong, but yeah, anyway, so let's try if it's working or not. Okay, so because it showed me an error on the screen, so I think we did something wrong. What we did wrong? Okay, I'm not sure. Let's try again, and I'll show you the error. So it's saying record must have minimum 2 subentries, not 1. And it's telling us for all the um, mappings. Let's search for that. Okay, we don't have any reference for it. Interesting. So we did something wrong, but we don't know what we did wrong. Yeah, it's weird that doesn't have any kind of parameters here. So let's use this tool here to open up this one. Okay, insert. Okay, hopefully. So that tool is basically filling all the missing parts for us. So it might be possible that we missed something or our file got damaged somehow. So that just make that for us. Let's try again. Again, the same issue. It's basically telling us the record must have 2 sub. So what I can do here is I can remove all the mappings and all the related um, TPDO and RPDO settings. Yes. Oh, it's ran to probably bug. So if I find the reason, I'll share it with you. Okay. I mean, I'll update the repo. Probably there is a problem in the repo. So let's stop it very quickly here. So we have it here, and basically, oh, they appeared. Our PDOs are okay. So let's generate it. Okay, again, same error. It says 1, 6. Remove it. Remove it. And let's add them again. They are ready. All right, you see, probably it was a damage because I was working on this for a while, so I might damage this. So I'll update the repo, so hopefully you won't get into the same problem. So I'll do the same for these guys here, and I reset them to the normal parameters. Let's try again. CANOpen. All right, yeah, perfect. That's worked. So let's go back and let's run it. So now what we expect here is that we gonna get a value for now is 0 probably every 1500 millisecond. Let's see it. Okay, let's scan the network or set the heartbeats, and let's wait. Okay, so there is an issue, and the issue is that we didn't activate this. So when you click on here, you should press this invalid one. So basically it will activate that, and the CANOpen object ID for this is 180 hex. So let's save that and let's go back. So what the hell? Why? So maybe there is a issue in the code. I'll need to fix that, and hopefully you won't run into this issue at all. But for now, I need to do this again. Not the first one. Okay, insert profile. Insert. Okay, worked. Let's run it. Yeah, here we go. So we have the TPDO1 transmitting every uh, every 1000 is supposed to be every 1000, but it's transmitted once. So let's see what's the issue here. So the good thing about this kind of tutorial, I mean, it's very boring, obviously, but the good thing is that I'm running into issues, and you'll see that how I proceed with solving the issues. So it's transmitting only once, and that's weird. So first thing we need to check is that, do we get operational? Yeah, we get operational from the um, CANOpen stack. So it means that the node is working. Um, but what can be the issue here? Interesting. Mm, oh, sorry. Why this is changed? Yeah, this is the problem. So we calculate that and we put it at 5 DC. So 5 DC. I don't know, for some reason that changed. Oh, that can't be true. Okay, so it says again, record must be blah, blah, blah. So let's remove this at least. So I think there might be an issue with these guys here because they are not assigned. So we have made a PDO which is not basically assigned to anything. So probably that's the issue. So same thing for the RPDOs. Remove them. I think then it makes the problem. Yeah, I think that's gonna fix the problem. Yeah, so that was the issue. So it's just the XPD file that I generated, so probably it had some errors. So all right, so I think hopefully that solved our issue, and let's run it. That was the issue just for the errors that we were getting, not the TPDO issue. So the TPDO issue was that for some reason that variable there changed to 0, and when it's 0 it means that it just generated once. And close this, and now it should be fixed. No, again there is an issue. Okay, I didn't save this, so 5dc save again will generate the file. Yeah, this object dictionary is a bit troublesome. If I found some extra time, I might start to work on that and fix these issues. But yeah, so for now we just didn't click on save. Apparently you have to do that, and that's why we didn't get the TPDOs. Please. Yes, now it's working. So sorry for that. Okay. So, and here you can see every 1500 we're getting the TPDOs and the value is 0. Okay, let's change that. So what I'm going to do here is basically just go here and let's say I'm gonna put, I don't want to make it complicated because it's not good to put 10 millisecond delay here, but I don't want to make things complicated for now. I just put a 10 millisecond delay for now, and then let's access that variable. Okay, so in order to access that variable, it's a bit tricky. Let's open here. So it's in the C file. So the variables that we generated, which first thing is that we should check where it's generated. So that variable, I think it should be in process. Okay, we put it in the RAM, but we don't want to be in the RAM, so we just put it per syscom and then save and generate the file. And there we go. So it's generated. Now, if you want to access that, it's simply you just go back to your code and then you write it od per syscom. Sorry, yeah, that's it. And then x, I think we put it 6,000. Uh, let's see if we can find it. Let's check it because we cannot find it. Should be there. Yeah, it's here. But for some reason it's not showing it now because maybe we need to reindex the files, probably rebuild and freshen all files. Hopefully that will fix it. Persistcom x6000. Yeah, here we go. We have it. Now we just increase that. That's it. So let's run it. So it said od persistcom. Okay, because we need the od.h file here. Include od.h. Is it? No, it should be od.h. So let's run it. Okay, yeah, here you go. You'll see it's increasing. So, but the thing is that you're seeing it every 1,500 millisecond. So that's why you see big jumps. Okay, but that's fine because it's just increasing right on time. And again, even considering that 10 millisecond delay that you put there, you still see that this is working perfectly. So it's sending the information right at the time that it's supposed to send them. Okay, so that's perfect. All right, so that was one of the things about TPDO. So I just transmitted that TPDO and it's working perfectly. So let's close the extra things that opened. Um, but this is not the perfect way to transmit TPDOs. I mean, I usually use this, okay, in parentheses. But this is maybe not the best way to do that. So let me go back to the code. So another way to do that, let me just open my notes because I took a note from this. Okay, so another way to do that is to use this function, odis underline set u32. So why we do that? So first let's use it and then I'll tell you. So it said which object you want to change. Okay, so we say OD find from OD that we have. Okay, the object dictionary. We want index 6000. Okay, so we want to change that. And which index we want to change? Same index, like we don't have the index because we didn't use the arrays there. Okay, so it's just simple value. And what value we want to write there? We want to just write, let's say, 1 2 3 for now. Okay, don't want to make it complicated, so let's comment this line. And then this OD origin, what was that? See references for set value. Okay, set value help us. What is this OD origin? If true, the potential IO extension on entry will be ignored and data in the original OD location will be written. Okay, so the thing is that if we call these functions instead of writing directly to the variables, if we set something, for example, if we said, I don't know, like I, we extend it, so I don't want to get into the details, but extensions are some stuff that you can add to objects in your object dictionary, basically to do extra stuff. For example, if you want to change this value, then probably some values are also depending on these values, so they will change as well. So the CANOpen stack can handle that, but I'm not going to use that here, and I didn't use it honestly up to now. But calling this function will basically go through a routine and then handle those situation, and then finally update the OD value. Okay, so that's the reason that we might be that we might think about that. Okay, it also changes, check, you see the data length and everything else, so it's pretty safe way to update a variable in the OD dictionary. So that's the reason. But here we don't want to do crazy stuff, and we don't want to do the IO extension and all this stuff, so we just put it false here. And I think that's it. Let's run it. But I usually use this way, honestly. Can open here. So yeah, we have 1 2 3. You see 7b 1 2 3. Okay, so that's another way. What else? Yeah, that's it. That's it. So let's do one more thing. Let's disable the auto transmission of the TPDO. Okay, and we want to transmit it whenever we want. So we put it 0, save, export, and we saved it. Okay, so now if you run it, probably just transmitted once, probably no, definitely transmitted once. Yeah, and then that's it, we don't have it anymore. So, oh sorry, we have it still. Probably I didn't save it again. That's so bothering. Or maybe this is a software bug, I don't know. So I just save it just for checking. Yeah, it's saved. Export. And let's clear here. Okay, we have the TPDO. Okay, this. Okay, yeah, yeah. So it's right, because the only reason that you saw it 2 times, it was that in the process of programming it reset the microcontroller 2 times, so that's why you saw 2. But yeah, that's it. You see, once we receive it, and that's it. Now we want to trigger the TPDO to be sent by ourselves. So what we do is that we just come to the code here, and we say okay, we say CO So these are the things that I found it myself, but I just tell it here. I don't want to show you where I found them, but just here we write TPDO send request. Okay, so we want the CANOpen node to transmit a TPDO for us, and we tell it, okay, which TPDO you want to send. Okay, we want to send CO, which is the CANOpen node, but we can access that like this as well. So we can say CANOpen node STM32 CANOpen stack, and then we say TPDO, and we want the first PDO to be transmitted. Simple as that. Let's run the code. So now, let's see what's wrong. Oh yeah, this is not a pointer. This is the object itself. So let's run it. So now we should be able to see this TPDO sending every 10 milliseconds. Yeah, you see, every 10 milliseconds we have a new PDO because we are updating the variable, and then we just ask it to send it, and then we wait 10 milliseconds, and then we do it again. So that is the way to transmit PDOs manually. And just one quick note here is that we don't have um, uh, this observation here. So in some stack you have something that we call it COS trigger, change of state trigger, and in those cases the stack will basically monitor a value and then transmit it when it changes. Okay, but we don't have that in CANOpen node because regarding the standard for CANOpen, it shouldn't do that. So it was an extra thing others implemented. So if you want to implement that, you should consider it in your code. So for example, here you put a if, and they say if persist com, for example, x 6000 was not same as, let's say, old counter, it means that it changed, and now you transmit the TPDO. Okay, so this is how you handle uh, a change of state solution situation. All right, that was the thing about the TPDO. So now let's talk about RPDOs. Okay, so in order to do that, I'm gonna use the F0 one. Okay, so in F0, I'm gonna make a RPDO which receives the this TPDO. Okay, so um, let's do one thing. Let's do a chain. Okay, so let's transmit this every every 1500 millisecond. Just check it. Oh, see, you should click here first, and then you should change that. Okay, export. All right, we should have the TPDO working now, and it should be going up. Yeah, you have it every 1500 millisecond, and yeah, you'll see it's going up. So now we want, so this is TPDO, or a sensor value transmitting in a network. Okay, now the next step is to receive this, right? We want that on another node. So let's go to the F0 one, and let's open that also in the object dictionary editor. So the this one is in this folder here. Okay, so we have this new product called, so let's change that to costume. So let's call it no, uh, board for tutorial. Okay, just calling it a name. And here we will make a new variable, and we call it, just for the simplicity, we give it a hex address, and we give it the name counter from G0. Okay, so funny name, but yeah. And then we give it to save it in persiscom, and we give it receive PDO access, and save it, and we go to the, so we know from last time that we need to remove all this extra stuff. Hopefully by the time that you watch this video I fix that problem, but for now let's remove this. Okay, now you have counter from G0 in the RPDOs. Okay, so we'll make a new PDO. Then we need to give it a CANOpen object. Okay, so the CANOpen object for counter was I don't have it here. I should have it here. Yeah, it's 1A0. The reason is that it's coming from node 32, and we gave it 180, so it basically added 180 to 32, and that's coming to 1A0. So 1A0 is the RPDO, sorry, the TPDO ID. We can fix this as well if you want to do that, so we can fix it to 180 if you want, but here the node ID will be added to this, and then that would be the packet ID or the message ID. So for this test it would be 1A0. Okay, so let's go back to the CANOpen editor. We enter 1A0 here, so we receive any message with 1A0, and we'll map it to counter from G0. Here we go. So we just need to make sure that this is unsigned, so it's the same as TPDO1, and here we have it configured here, and let's save it. Okay, let's go back to the IDE, run it. This is the F01, okay? Okay, we need to monitor that variable. So what we can do here, first let's run the code. And let's see if it generates any error. No error. And let's set a heartbeat of 2 seconds for it. Yeah, we have it. It's working. It's 24 one. And let's see the variable here. So live expressions. We want to see OD. What was it? Forgot the name. So let's go back here to CANOpen and OD.h. So it would be OD per syscom. Let's find it here. So it would be OD per syscom, and then it would be x6. We need to refresh again. Whew. Index version of files. Oh, come on. Index rebuild. Okay, that's weird now. Why it doesn't show us? Did we? Oh, we generated over. Ah, hell, that was bad. We generated over that CANOpen tutorial that we were doing, so it's still fine. Or we didn't we? So we are working in this, and then here. Yeah, we didn't generate on this. So we generated here, and then we generate this one back on the costume board. Yeah, we generate that on the costume board for some reasons, I don't know. Or maybe we didn't even generate it, so I don't remember. But let's freshen the files. So we generated the OD for STM32F0. Now we should see it. Yeah, 6001 is here. So I just put it down there. For now, probably it doesn't detect it because we need to, as we change the OD file, we need to generate the code again. Let's do that. Let's check it if it's transmitting any errors. No, we don't see any error. That is just the error at the beginning when it turns on, and it's an error reset. Basically, it said all the errors are reset. So what we want to do is now we'll debug it and see that RPDO. It's not working for some reason. So we have this 180 going in the network, right? Or we don't have it because other nodes ran into some issues because of resetting the other node. So the other node was resetting, and it probably ruined the canvas. So I need to do com reset on all of them. Okay, now we have all the nodes except for one. Let's reset all of them. Okay, we have them working except for 24 that we are debugging. Okay, so now just let's check if we get the TPDO in the network. It's not coming in because 32 is not generating heartbeats. And it basically tells us that there is a problem. Let's do a reset again. Oh, we are resetting it. Let's see. Okay, now we have the TPDOs transmitting here. Okay, it's working. And now let's continue this code. Yeah, you can see the value is increasing here. So basically, we are getting a TPDO and transmitting over the network, and then this node is taking that value and sampling it here, so you'll have access to this counter. So this counter is basically coming from G0 board, and we are getting it on F0. So that was RPDO, and that was simple, I think. Yeah. What else we can say? Mm, okay, so let's continue. So up to now, we have a working node. So we have 3 working nodes, and they are basically in operational mode. And then we have also one PDO transmitting every 100, every 1500, and we have another node which is 24 here, which is STM32 F0, and that is basically sampling that TPDO value. Okay, so we can see that value here. So that is a working network for now, and now let's make it a bit more complicated. So let's do one thing. So what we can do here, just let me think. So let's write a code that change the just let me have a look here. Let's write a code that change the value of this TPDO, not this TPDO, but the counter which is connected to that TPDO whenever the code runs. So basically, this F0 wants to reset that counter in the G0 board. Okay, so we want to do that in the SDO way. So we want to have a direct access to that and change that. So let's do it first with the CANOpen Magic. Okay, so in order to do that, I'll add a write to node, and then I'm gonna choose node 32, and I'm gonna select custom entry 6000. If you remember, our value was in the counter value was at 6000. So let's write that 000, and let's have a look here. So it's now this value, and let's write it. Yeah, you see it started from 0 again, and it's going up here again. So this is basically a SDO download. Okay, so if I close this like this, and then if I just filter stop filter the PDOs, and also stop filter the SDOs. Okay, if I do that, you'll just see the no, still I need to sorry, I need to stop the heartbeats from going in. Okay, so if I press this button, you'll see the whole SDO communication. So basically, the first thing is that it asked the SDO client, which is the CANOpenMagic and PCAN um, device, asked the Node 32 for SDO download request, and as we just wanted to write 0, so it's like 1 byte only, or here, sorry, here it's like 4 bytes. We just expedited that. Okay, so by expediting is that we just ask the device to do it immediately if it can, and here we got the response. Okay, yeah, so let's do the same thing, for example, for node number 1. So just let's remove everything, and node number 1. Oh, because it doesn't have the object. Okay, so it doesn't have the object, so basically it didn't accept. But here you can see, so we ask the just ignore the errors, because I know this board has some kind of errors in the controller. But if we just ask the node to node 1, so you can see 600 plus the node ID, so 6,601, to do a download request in expedited format with 4 bytes, and it's just responded that object does not exist in the object dictionary. So that's perfect. So all right, so let's do the STU. Now we did it with this, and now let's do it with the code. Okay, so in order to do that, we need to study the code base a bit. So let's open CANOpenNode, and let's go to the SDO part. And we are talking about STO client, so we'll open this STO client here. There should be some code. Yeah, this is the code for STO client. So basic usage, you see. So this goes to .c file, and let's just copy that. Let's put it here. What happened? So this part is okay. Why it's showing an error? Let's see. Okay, it doesn't know SDO client. So what we should do here is to include CANOpen. I think that will fix the problem. Not yet. Why is that? SDO client include CO. Alright, so we should include CANOpenNode 301 SDO client. Does that fix the problem? No. And why is that? SDO client. Oh, I think we have to activate that. So, alright, so in order to do this SDO, let's see what we should activate. Okay, so the configurations are usually in the driver target, and here coconfig. Let's check the coconfig file. We should have some configuration for SDO clients. So let's search SDO client enable. Yeah, here it is. So here we get the coconfig SDO CLI, and we'll go to our target, and here we'll define it, and we want SDI enable basically. Let's see if that solved the issue. Somehow the only problem is that there is an error somewhere. Okay, it didn't still detect the CO54 thing. So what's that? Maybe there was something here. 54 segmented. Yeah, we want segmented transfer. So let's do that. You can read about segmented transfer. Or this, and let's see. Still not. Okay, still runs the CO5, so let's see how we should enable this. Most probably there is a configuration, there is somewhere we should activate this FIFO. So let's see that if we can find it. Let's search through the files for FIFO. Oh. Let's search it here in all the files. Okay, this is deactivated. Okay, so there is CANOpenFig FIFO, and let's do it here. So define, and then you need to activate the FIFO. Still, still problem. Let's see. So the FIFO problem solved now, but still it doesn't detect. All right, where is the semicolon there? Right, I think it's fixed the problem now. Excellent. So I think that fixed the problem. Okay, so now our code builds, and now let's use it. Okay, so what we want to do here, first we need to let's say write SDO. So in order to do that, I just write SDO, and then SDO client will take that later. So no, actually we can do it now. So CANOpen STM32 has a pointer to so sorry, I should do this CANOpen Node STM32. This is the variable that we have here, and that has a CANOpen stack properties, and where we can find the SDO servers, maybe? No, don't remember what was that. SDO client. Think it was, let's see, it was the SDO server, probably. Yeah, most probably it would be this one. Let me see. SDO, we have it enabled, no? Yeah, we have it enabled. So let's just check it again. Interesting. Why we don't have the SDO clients here? That's very interesting. Let's find it. I'm deliberately doing that, because I would like you to understand how I go through the code and find the problems. So it said if the config SDO CLI and CANOpenFig SDO CLI enabled, that it had this one. It should compile here, but why it doesn't do that? Interesting. Maybe Maybe it's the problem with this one. Let's see. See config, but I did this. So what can be the problem? Just for checking, let's do this here maybe. Define just for checking. Config SDO CLI. Sorry, just take this code from here. Maybe I did something wrong. Does that activate this? Apparently not yet. Why is that? Still client. So it's working here but not working there. That's interesting. Okay, so a steel client init, and here setup, and let's see what it does here. So I should have a clue in.c file. Interestingly, this is not activated as well, although we have it here. Let's close it. Let's remove it from here. Hmm. Just put it back, the FIFO back. What is the issue again? Okay, it doesn't detect this, it's fine. We just want to find the reason that this is not getting built. So what I do is that just go through the CANOpen app configuration part, this part specifically, and there should be somewhere here in the init function specifically that it should initiate the SDO client. SDO, so yeah, we have it here, but Why it's not? So this is enabling STO client. Sphere, flag, blah blah blah. So apparently this is defined here as well. So maybe that's the issue. Let's just see. Okay, interestingly, apparently that was the issue, but it shouldn't be that. Let's see if we have access to the STO client objects now. STO, no, not yet. Okay, now we should have it actually. So it should be here. Probably we need to freshen the files again. Yeah, here we go. But the thing is that that wasn't a good way to solve this issue, because if we defined this before, then why you're defining it again? So very interesting. And apparently now it's okay. Okay, so let's see. Alright, so we write SDO with a STO client 0, because this would be an array of the 3 or 4 STO clients we have. Then node ID is going to be, which node ID we want to write to? The one that is generating the TPDO. Node 32. Which will be 20. Index 0x6000, subindex 00. Date we want to write is 0. Data size will be in 8. Oh, sorry, 1. So every time that we reset the code, it should write that. Right, again the problem. Argument 1 is wrong. It's because, oh right, CANOpen stack. Yeah, we need the address for this. So here we don't have the US one. I don't want to spend time on that, so we just wait 1 millisecond, but you need to do that in the microseconds. Okay, let's run it. Let's see what happens here. Let's filter the irrelevant nodes. Let's see. Yeah, you can see it start always from 0. Oh, sorry. I was resetting a wrong microcontroller. There is a problem. It doesn't send the SDO client request. So most probably we passed a wrong SDO. I don't remember if it was like this SDO client. Let's see what is SDO client. SDO client, SDO client. Oh, sorry. Yeah, I think it needs to. It's not an array. I don't know why I thought it would be array like TPDOs. Probably it's just a STO client. It's just a basically a structure, and probably that we don't need that as well. So let's just see if that will work. Yeah, it didn't work. So just now it should work, unless we did something wrong somewhere. Interesting. Let's reset everything, every node in the network. Right, they are all in the reset mode now. So what we did wrong here, we need to check that. Okay, so we passed in the SDO client, and it says star, so basically that's fine. So let's debug the code now. Okay, we have the SDO client here, so now let's see why it's not running. So it's SDO client setup. What ID we have? We wanted to write to. Wait, we have a problem here. Yeah, we are writing to 32, right? So, yeah, we are writing to 32, so that's fine. Initiate the download. SDO client is also working. Field data. So it's saying client abort, but nothing transmitted in the network, so that's weird. So maybe something is wrong, really. Let's go into this. think something is going very wrong here. Um, so I think, did we set the right variable there? Just let's check. What does it need? Oh, it needed data as a pointer. Okay, so that was my problem. Let's make a 32-bit temp, let's say 2234, and then, oh no, not in the G0, sorry, in the other code. And then here I gave it a address. Am I doing something wrong here? Maybe. So it's data and then size, but I did something wrong somewhere. So this is 0 and this is temp. Okay, so this is still client, and then we're passing a variable there, and the size of the variable is 4, and let's try it again. Here we go. We have it, at least up to now. We have it transmitting. Okay, so let's see now what's wrong there. So STO abort by client, STO download request. So we send a request to update 6 times. Oh, we should stop seeing extra stuff. So let's see. Here we did a STO download request to node 32, and SDO aborted, basically. Sorry, timed out means that 32 didn't respond. Interesting. So let's have a look at the OD file. So we have the read and write access here, and we could change that. So let's try again, see what's exactly. Expedited 4 bytes. Yeah, it seems correct. But why we are getting a STO protocol timed out? These errors are emitting from node 1, which I told you it has some problems. We don't just care about it for now. Let's think about it. STO is transmitting, so that's okay. So let's do the same thing here. Interesting. Oh no, sorry, we should have selected 20. Interesting. Why 20 is rejecting our write request? Twenty read 6000 index 0. Let's read that. Protocol timed out. Very interesting. Read. Oh, okay. Now it's responding. I just reset the node, so I don't know what happened there. I have to add a look. So let's write. Yeah, writing is also working. And let's write with the other node. Yeah, that's work as well. So let's see. Let's disable it for now. Let's put it on fix. So we have a TPDOs and like that is going forward from the G0, so it's transmitting in the network. And when I reset the F0 board, that should reset this value. Okay. Why it didn't? So let's try here. Clean. Yeah, it actually does, but as it's going very fast, we don't see it. So let's see, reset. No, from the node that I have, this doesn't go. Why is that? What value we are setting to it? We are setting a value other than 0. If you remember, we are setting this value. So let's put 0. Let's run it. Okay, so it's transmitting in the network. See the value here? And yeah, it started from 0 again. So you see, not exactly 0, but you see that it's started from the beginning again. So that's the writing part for the SDO. And let's do now the reading part. So what we can do is that we can read the device type of 20, which is 1234 hex. So let's do that. Okay, so let's make a global variable for our own convenience. In 32 G0 status, device type. Put it to 0 at the beginning, and then let's come here, and just for the beginning, let's do read STO, and then same as the previous one. So CANOpen STM32 can stack STO client. So this is the thing, the STO client that we have. Node ID is 020, index is 0x. Let's see. 1000. 1000 subindex 000 actually, and let's write that to temp again. Buffer size 4, read size 4, and but let's just read quickly. What is the read? Read size is the value that it gives us of how much it read from the node. So what we can do is that we can write it here. 32 amount read. Amount read. For temp, we can just not pass the temp, just directly pass the G0 device type. So it basically read the from the 20 node 20 hex, we'll read the device type and keep it for in G0 device type for us. Let's see. Again, we have this asleep microsecond, which we remove it. I'll delay, although I strongly suggest you to implement that the microsecond. It should be very quick and straightforward with the DWT, but it's out of scope of this tutorial, so I just stick to what we had to discuss. Okay, so let's do this. So let's add it here, G0 device type. So we're getting 0 at the moment. And why is that? Again, the node will need to be reset again. Oh yeah, we got it. We just not needed to reset the G0 board, because you know the problem in my network is that this STM32 F0 that I have, basically when you reset it, it will be float for a while. I mean the transmit pin will be float, so it will transmit some random errors, and that basically put the STM32 G01 in the error mode, and I don't have the code for error handling for that one. You should have that actually, but then you just basically reset the microcontroller, and then you can basically read the values, and the CANOpen will work as it's expected. So let's do this, and then let's check here. 0. Let's do it. Now I reset everything and I do it. I put that a node in the reset mode. So maybe that's not the best way to read that, because they always put that node when you reset the board. It put the STM32 G01 in the reset mode. So, or maybe actually can do one thing. Can reset them all together. Let's just run the code. Right, it's running. And now let's reset the whole network. Let's see if it took the right value. Not yet. Oh, actually it's not responding. Oh, that's the issue. I should have just waited a bit here, or something like this. Just passed in the wrong amount of time. So it's kind of late here, so that's why I didn't have a very good focus. Okay, let's go to the debug mode. Run live expression. It managed to read it, but just let's reset the whole network again. So reset, checking again. Yeah, it managed to read it from the G0. Okay, so even if we change that, let's say we write it to another value from the CANOpenMagic 4321, right? Oh, it's read only, so we cannot change that. Okay, but yeah, even if we could change that, then if you were running the code from here, it would be changing that. So yeah, so I did. So we did the writing part, and we did the I don't know why. Oh yeah, it's we did the writing and we did the reading of this. You just consider changing these to microseconds. Okay, this one and this one, to be more efficient, like for the code to be more efficient, because that basically affect the overhead timing that we have over the communication protocol. So that was the SDO read and write. What else we have to cover? Let me just think. SDO. Okay, we can talk about the node guarding now. So node guarding talks about a very interesting idea that a node, let's say here we are talking about the STM32 F4, it will guard against another node's heartbeat. And if it doesn't receive another node's heartbeat for, let's say, 3 consecutive, um, uh, let's say, heartbeat period, it will change itself to or pre-operation, so it goes out of operation when it doesn't receive the heartbeat from other node. So let's activate that. I don't clearly remember how to do that, but we can try. So consumer heartbeat. So it said set to 0 for bit 24 to 31, and then 60 to 23 node ID of the monitored node. If 0 or greater than 1, that's not used. Okay, and then 0 to 15 heartbeat time in millisecond. Should be higher than corresponding person. Okay, so I would say it's pretty straightforward. So it said basically the bits 24 to 31 should be 0, and then 60 to 23 should be the node ID of the monitor. So let's go to the first one and let's do this. So this is 31. So let's open calculator. 0, binary 000, doesn't matter the rest of zeros. I forgot again. So 31 to 24. So it's to 31, and this will be node ID. Okay, so let's do this first. Heartbeat time in ms. So we say after 4000 microsecond, if you didn't receive anything, that's bad. So 4000 would be FA0. Okay, so the first part would be FA a 0. Okay, so this will be the 16 first bit, so 2 8 bits, and then the node ID of the monitored node. So we want to monitor G0. G0 is 20, so it would be like this. So it's from 16 to 24, which will be 8, and then the rest should be 0. So like this. Yeah, like this. Yeah, let's do that. Oh, I pressed the the Control S first, and then I want to do the save change, but that was wrong. So you do the save change and then you save the project. So yeah, I think it's it. So these first two are, what was that? So first 2 bytes are heartbeat time. So we set that, and then the node ID, and then 000. So let's generate the code. Oh, same issue again. No, it's another one. It said error converting blah 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 to type unsigned 32. So unsigned 32 is wrong. So let's do this. First, let's do this FA, and I think that's it. No? Or maybe we should do this. We should enter not hex here, but actually we should enter decimal value. So it would be this number, 135,072. Okay, this time no errors. Perfect, let's try it. Okay, so now 32 is transmitting a heartbeat. Let's see that. If it does, yeah. 32 is transmitting an heartbeat. And if we configure 24 to guard 32, we should receive an error when the 32 is not on the line anymore. So let's stop the 32 from transmitting. I stopped it. So you see, this one doesn't transmit anything. And we should receive an error for the node guarding unless we miss something. Yeah, we missed something definitely somewhere. Let's go back to the code once again. First 2 bytes are 0. Let's do it in hex just in case to make sure it's okay. 0x. this value, and let's put that in actual value as well, because I'm not sure if that's gonna be the value. Right, so I think that's it. Let's try it again. Let's run it. Okay, so nodes are working. Now let's stop node 32 or 20. Nothing happens. Okay, so node guarding still not working. Let's have a look. So according to the description here, the first 2 bytes are for heartbeat time in MS, and we wanted that to be so 4000 millisecond. So that would be 4000 millisecond. That would be FA0, and then I think we missed a 0 here. Okay, so that would be 8, and that's 8 bit, and that's 8 another. So we have 3 8 24, and then the rest is also 0, which we don't show it here, but we can just put that here, and that's it. Let's try it again. Okay, let's see. Set heartbeat, and let's clear here. So we have nodes working, and now we just press this reset button, so these nodes stop transmitting. And yeah, here we go. We got lifeguard error, heartbeat error. So this node changed to pre-operational. Doesn't matter if the other nodes come back again. This node will be pre-operational, and the only way to make it out of this mode is to instruct it directly to go out. So like this, and then we'll start doing normal behavior until, so again, you see the heartbeats are going in and everything is fine. If I keep the reset of that board, after 4 seconds this change to lifeguard error and stops there. Okay, so that's node guarding and heartbeat guarding basically. Perfect. And for the last part, what we can do is to just transmit PDOs um, ourselves. Basically, we make a PDO and we transmit. It's nothing very different. So basically, for that, we just go here. We make a PDO. Sorry, we make a PDO. So we say PDO, manual PDO. Let's say for the sake of this tutorial, I just make it a record. So there is a difference between array and record. Array should be this, like all the elements, child elements should be the same type as the they should be same type, either 8 byte, sorry, 8 bit or 16 bit. But if you make it record, you can have different types of data. So yeah, I usually use records. Okay, so manual PDO, and then we will give it something like this. And then we'll make 4 objects, sub objects basically. So this will be byte 1, byte 2, byte 3, and byte 4. And consider that they are all bytes, so I should change their type to uint. And you can do that, you can just make the, like, if you are having 32, you want to send a TPDO of 32 bytes, you can change that in your code. Okay, so now we have all those. We'll change the PDO to transmit for now. Okay, and now we'll map it to a PDO, let's say 100, 300 something, plus the node ID. Okay, if you want to not use the node ID, I think you should add a 7 or 8 here. I don't remember that, but you can check the documents for that. But yeah, if you don't put anything, you just press put this, it will add the node ID to it. And we don't want to have an event timer for it. And by the way, read about inhibit time, and it's very handy feature if you have a huge network of devices sending data regularly. Okay, you can check that, it's very useful for that. And the sync start is basically when you want to transmit an information after you receive the sync. So you specify the time that after sync you want the data to be transferred. So, and that's basically respect that. Okay, and then we want to transmit basically byte 1, byte 2. As I said, you can make all this in one uint 32 integer, but here just for the tutorial I'll just did them separately. Okay, so now we have it here. Save, and let's go and export it. Okay, perfect. Freshen the files. So we have access to OD. So OD persistence com. Oh, sorry. Here we have access. What was the manual PDO 6020? Didn't reflect the changes yet. $6020. Because probably yeah, we saved it in the RAM. Alright, make it again. We want it in OD persist. Just freshen the files once again. $6020, here we go. And then byte 1. So I put byte 1 0f1, and then byte 234, F2, F3, just as an example, and then 2, 3, 4, and then if you remember, we had this CO request, CO TPDO send request, and we know that it's TPDO number 1. So we say CANOpen stack TPDO, sorry, 0, because it's the first element, and as we run the software, it will transmit the first TPDO as we wanted. So what's wrong here? Oh, sorry, I need to put it like this, and yeah, here it should be like this. What's wrong here? OD persist com, yeah, because we didn't include the object dictionary here. What else? Of course, because this is going to be like this. Run it, and let's wait for it here. Should be TPDO 3 of node. What's wrong? COTPDO request. Let's see. Let's disable all the nodes except for 30. Sorry, what was it? 23, I think, right? 24. And let's reset the 24. Why we didn't receive the TPDO? Interesting. Operational, it's still operational, but why we don't see? It's waiting for the, it's because of node guarding, it's go out of operation. Let's deactivate the node guarding. Okay, so what's the issue here? Let's see. Maybe TPDO. So TPDO 1. It's perfectly configured. PDO. Oh, we didn't. No, it's fine. So it's 380, 24, 254 inhibit time, sync value, and event time. So why it's not transmitting now? Let's think about it. So these are all transmit as well. So technically it's okay. The only thing is that why it's not transmitting it. Let's go to the coding and let's go to debugging mode. Let's see. Up to here everything seems fine. Okay, send request 1, sync value, sync counter, inhibit event, blah blah blah. So let's see. So TPDO it's 380 DLC4 buffer blah blah blah. So why it's not sending it? Okay, so let's go and find the root of this problem. So we have a timer here that basically handles that. So handles the PDOs, okay? So we stop here and or maybe here, and then we'll see what it's saying. NMT is operational, definitely. Yes. And then process TPDO I. So we have how many TPDOs? Why I did that? How many TPDO we have? One. Okay. So let's do this again. 5 F5 to go in. And then run it. Stop it here. So let's see the TPDO that we wanted to send to see if it's sent or not. Send request 0. It means that it's already has been sent in the network. Maybe we are doing something, or maybe we are not monitoring it wrong. It's operational. And now we do reset. Send request. Uh-huh. Actually, that's something else. Where is this coming from? RPDO guarding. Uh-huh. It's the rest of nodes that they are all in stop mode except for this one. And the thing is that why this one doesn't trigger TPDOs. There's something wrong. Again, we go to the process TPDO and we put a breakpoint here. So resetting, and first time that it reach here should have a PDO ready to be sent. Again, I run it. Wait, let's see what happens here. Oh, it's using some of the PDOs. Oh no, sorry, that's weird. So, or maybe it's busy with the SDOs from the moment ago. So it mix everything up. So just to make sure that these does not get involved in here. Okay. Data length map object, all is correct. Yes. So now it should. Oh, why didn't send it? TPDO. That's for request TPDO. This is for transmitting. Okay. This is send request, and this is. Okay, let's see here. Why it doesn't send it? CAN-TX buffer, and CAN-TX buffer is data is 0. Let's say it's yes, it's correct. Okay, nothing so far. You know what? I decided to do something else. So let's transmit it regularly to see if um, transmitting correctly. Mm-hmm. 3F0. Save, save, save. Now let's run it. Now we should see that coming here. If not, there is definitely something wrong. Okay, it's not. No, actually we see it here. Yeah. So this TPDO is coming from 380 with the values that we wrote F1, F2, F3, F4. Let's see if I can hide the network errors. Okay. There was something we could hide network errors. I can do it here. Stop filter. No, maybe not here. No, that wasn't here as well. Preferences. Yeah, show reference. No. Okay, so now we know that our node is basically transmitting that. So the configuration of the PDO itself is correct. Now the reason that we cannot send it in the first place, let's see. Let's put it here. And let's put a delay here. And let's deactivate the auto send from here. Save. Yeah, we get it here. So probably we didn't look carefully last time. So let's now just put it there and comment here. Or, I think we put it there after, I mean, we should put it somewhere that it will get transmitted after the operational mode. And we change the operational mode after a couple of milliseconds passed from the beginning of the code. So that might be the issue. Let's see. So we reset that node. Yes, you see, we received the boot up and then immediately we got the data that we wanted to send. So that's how we send the TPDO, custom TPDO. So yeah, that was this tutorial. I might record more videos, uh, but I think this would be enough for the start. And yeah, I hope you enjoyed it. Um, yeah, I didn't prepare anything because I just wanted to show you how I proceed with the debugging and everything. So the reason was that. So I hope it would be helpful for anybody watching this video. Thank you and bye.